So, with that, please help me welcome our speaker for the morning, Dr. Douglas Leonard, Associate Professor of Astronomy at San Diego State University. With a BA in Astronomy and Astrophysics from the University of Pennsylvania, Dr. Leonard earned his MS and his PhD in Astrophysics at the University of California in Berkeley. Prior to joining the faculty at SDSU, he accepted an appointment as a National Science Foundation postdoctoral fellow at Caltech. Dr. Leonard's research interests include the life cycle of supernovae progenitor stars, and the geometry and physics of supernova explosions as revealed through spectropolarimetry. Try that one twice. Currently serving as outreach and media representative at SDSU, Dr. Leonard is a dedicated science educator. He has contributed to several BBC Horizon and Science Channel videos on black holes, cosmology, and the death of stars. Dr. Leonard, welcome. Welcome to the Greenway Talks online at Palomar Observatory, and thank you for taking the time to speak with us today. We'll take questions at the end of the presentation. So right now, for that reason, I'll ask everyone to turn off their microphones. And with that, Dr. Leonard, the floor is yours.
Thanks so much, Steve. It's really great to be here, if only virtually, back at one of my old haunts, Palomar Observatory, many moons ago. As Steve just said, I was a postdoctoral fellow at Caltech, and I spent many nights and then days in the confines of the monastery, which provided observations that allowed me to opine about exploding stars far, far away and give talks like the one you see titled here, reporting on data that was obtained at some of the world's largest telescopes, including the Big Eye, of course, to try to uncover the secrets of very distant exploding stars, which are known as supernovae. But I'm actually here to talk more about a change that occurred about 4 years ago. A rather momentous event happened, and I bet you can all tell what it is just from this picture of me and my sons atop Snow King Mountain in Jackson, Wyoming. You probably have guessed that you are witnessing the very moments right before the great solar eclipse of 2017, which swathed across the United States in August, right here. And I'll just point out, if you're still bummed that you didn't get to see that one, just mark your calendars for April 8th, 2024, because that's the next great North American solar eclipse. So book your reservations for Dallas or Indianapolis or Cleveland or Montreal, because we're not getting one in Southern California. I checked the record. The last one we had here was in 1724, and I checked all the way through the year 3000, and there isn't another total solar eclipse visible for us here in Southern California. So until that time, you got to travel just a little bit. The experience made lifelong memories for my sons, of course. They got to meet an astronaut. Meeting an astronaut, I learned, is much better than living with an astronomer. But for me, the profound discovery was just how cool it was to actually see something astronomical with my own eyes and share that with my kids and with other people. Because up to that point, everything I had ever studied in astronomy required the largest telescopes like Palomar's to collect the faint light from very distant objects. And I thought, wouldn't it be fun to actually study something that you could just point at and say, hey, that's what I study in the sky, and where you don't need the world's largest telescopes to do the work. And so about a year later, I embarked on a quest to study the most famous star, I think, in the entire night sky, which is Betelgeuse. It's the bright, distinctly red star up here in the shoulder of the mighty hunter Orion. You can see a hunter in that pattern of stars, right? I can almost see it. Believe it or not, this is one of the most readily identifiable patterns of stars in the sky. And once you look at it, you can't miss it. Although this time of year, it doesn't actually rise till after midnight. So you have to see it in the wee hours of the morning. You'd think it would be really easy to study something that's so bright, but in fact, it's not. There are a lot of technical issues with trying to study the 10th brightest star in the sky. And I have over a year of my life to prove that it's hard to observe, because that's how long it took my students and I to reconfigure the equipment at our department's small observatory called Mount Laguna Observatory. Here are two of my former students standing in front of the mighty 40-inch telescope, which is currently the largest telescope on the mountain. But to reconfigure it so that it could actually observe such a bright star turned out to be a pretty tricky task. In case you're wondering, Mount Laguna Observatory is a 1.5-hour drive from Palomar Observatory in the Cleveland National Forest, about 50 miles outside of San Diego. Anyway, it took a bit over a year to wrestle the instrumentation into shape to properly observe Betelgeuse, but the timing actually was very fortuitous. It couldn't have been better, because just as we were coming online with our ability to observe it about 1.5 years ago, Betelgeuse started making the news. It became clear that this star was starting to do something weird. This is a headline from the end of 2019. And some headlines were even suggesting that it was about to do something quite dramatic. And the headlines continued into January of 2020. Okay. And by the end of the month, things were really ramping up to sort of a fever pitch. Things were getting very dramatic. I was surprised no one attempted to sell potions to protect you from the exploding Betelgeuse. The question is, why was there all this excitement? And to understand that, you just have to go back, 1,000 years, back to July 4th of the year 1054, when this happened.
Imagine the night when that colossal stellar explosion first burst forth.
So stars do explode. And if one were to do that as close as Betelgeuse, it would simply be amazing. This is an artist's representation of what it might look like. Suddenly, replacing Betelgeuse would be a point of light as bright as the combined light of a quarter moon. It would be clearly visible during the daytime. It would cast its own shadows at night. But how did we get to this point? Why were astronomers getting so excited at the beginning of last year? And why hasn't it happened, obviously? And what's our best guess about when it will actually happen? And so what I'm actually going to try to do this morning is give you the best answers we have to these questions. And it actually starts by just making sure that I remind you of our place in the universe. And that is by saying our sun and our retinue of planets is not alone. We sit inside a vast stellar system known as the Milky Way Galaxy. It contains over 100 billion stars like our sun, all bound together by gravity. We sit somewhere out here, far away from the center with all the other stars. And we actually orbit the center of our galaxy once every 250 million years. You probably noticed this isn't an actual picture of the Milky Way. It's a portrait. It's an artist's representation based on our best guess for what it would look like. And this is what it would look like, we think, if we should ever get a spacecraft out far enough and above the plane of the galaxy to actually snap a photo and send it to us. But we've never done that. And frankly, we're not even close. And the problem is distances are just so vast in astronomy. And as you probably know, astronomers measure distances in terms of how long it takes light to get from one place to another. So to give you a sense of just how big our home in the universe and then our ultimate universe actually is, if we start at home and look at the moon, the closest astronomical object to us, a place we actually have gone, yes, we have, which shines light by reflecting light coming from the sun. The moon's about 200,000 miles away from us, and that's about the distance that light travels in 1 second. And so that means when you see the moon in the sky, you're looking back in time 1 second, because it took a second for that light to reach you. And you could say the moon is about 1 light second away from us because of this. The sun, like all stars, it's self-luminous, it's a hot ball of gas. It emits its own light, and it's about 500 times further away than the moon. If you do the math, it's about 8 minutes, 8 light minutes away from us. And one of the amazing things of the past several centuries is astronomers have realized that all those stars you see at night are really just like our sun, but they're so much further away. This is the closest one, known as Alpha Centauri, and it takes 4 years for its light to reach us. So you're looking back in time 4 years when you look at Alpha Centauri. So when we return back to this whole collection of stars that make up the Milky Way, billions of stars, you'll see why we've never traveled outside of it. From end to end, our galaxy is about 100,000 light years across. We're about 30,000 light years from the center. The most distant spacecraft, Voyager 1, that was launched in 1977, is still less than 1 light day away from us. So not even close to the nearest star, not even close to getting outside of our galaxy. That said, we sit at a great spot for observing the rest of the universe here on the outskirts of the Milky Way. And when we look out at the rest of the universe, what we find are billions of other galaxies, each of which contain upwards of 100 billion stars or so. This is a picture of the closest major galaxy to us. This is known as the Andromeda Galaxy. It's about 2 million light years away. You can see it with your own eyes if you are in a dark spot and know where to look. And this is just a photograph with a good camera. Here's a nice shot taken by an Orange County astronomer of Andromeda. And this is the closest galaxy. But as we go further and further away, we just start seeing billions of them, and they just make for beautiful pictures. Each of these containing upwards of 100 billion stars. And what we've learned is that a very small fraction of stars, about 1 out of every 400 stars that nature mints, will end its life by exploding. And that might not sound like a lot, but remember, there are over 100 billion stars in a typical galaxy like this. And if you work out the odds, it means there should be roughly 1 per century or so exploding in a big galaxy. And since there are billions of galaxies in the observable universe, this works out to about 1 supernova per second somewhere in the universe. We don't detect nearly all of these, but we do catch several thousand per year at this point. Let me give you a sense of what a typical supernova looks like in another galaxy. In this case, a famous galaxy known as the Whirlpool Galaxy. It's about 23 million light years away, just in our backyard, very close. This is a picture taken in 2011. Galaxy was just minding its own business. And just to be absolutely clear what you're looking at, this fuzzy spiral thing, that's the combined light of hundreds of billions of stars, 23 million light years away. These dots that you see here are stars in our own Milky Way that are right in our face. They're typically tens or hundreds of light years away. So you're looking through a screen of Milky Way stars at this thing that's much more distant. Okay, just be clear about that. One day in 2011, to us, one of its stars decided to explode. And what it looks like to an Earth-based astronomer is that a new star, a very bright star, just appeared in this galaxy. And so this is kind of the before picture. And then I'm going to show you the after picture and see if you can spot the bright new star in one of the spiral arms, as they're called, of the Whirlpool Galaxy. If you don't see it, I bet you will when I blink the images. So this is before, that's after, right there. That's the supernova. Notice that's 23 million light years away. These guys are probably tens or hundreds of light years away. So it's rivaling their output, their apparent brightness. There's the before picture. There's the after picture. So we see these things all the time. Why did astronomers get so excited about Betelgeuse? Well, the answer is probably obvious. It's not 23 million light years away. It's estimated to be about 500 light years away. And what's special about Betelgeuse is it's exactly the kind of rare star that we think is going to end its life by exploding. It's a type of star known as a red supergiant. Red because it's red, and supergiant because it's huge. It's a humongous star, both in terms of its size and in terms of its mass and in terms of its luminosity, how much light it's giving off. To give you a sense of how big it is in size, here's our solar system. You got your basic sun, you got Mercury, Venus, here's Earth, there's Mars, and then there's Jupiter. If we replaced the sun with Betelgeuse, we would be inside of it. In fact, Jupiter would be grazing the outer atmosphere of this supergiant star. How do we know this? This is an actual picture of Betelgeuse. It's one of the very few stars that we've managed to actually resolve its surface. And so we know how big the star actually is. It's big enough and close enough for us to actually turn it from being a point of light into a resolved surface. So this is an actual picture here of the surface of Betelgeuse in the beginning of January of 2019, before it started misbehaving. Okay, so Betelgeuse is just huge in size. In terms of mass, it's also really big. It's estimated to be about 20 times the mass of our sun. And in terms of how bright it is, its luminosity, the amount of light that it gives off, it's estimated to be giving off about 100,000 times the amount of light our sun gives off. Stars like Betelgeuse are exceedingly rare. As I said, about 1 out of every 400 will ever progress to the state that Betelgeuse is in, nearing the end of its life. And at this point, Betelgeuse is poised to explode. How do we know that these stars explode? Put simply, we've seen it happen. In the last couple decades, we've now seen stars that look exactly like Betelgeuse end their lives by exploding as a supernova. Not in the Milky Way, unfortunately, but in other galaxies. Let me show you a great example of this. This is actually a very nearby supernova in 2008 called 2008 BK. It was only 13 million light years away. You can see the host galaxy, as it's called, here. And the supernova, when it was bright, is right there. And this is a very detailed close-up image of a small box around the supernova taken with special adaptive optics, where you can see the supernova here, and then you can see all the stars that are really nearby in the picture, in the field of view. The brilliant thing about this was that astronomers had actually taken high-resolution images of this exact part of the sky before the star exploded. And digging back through the archive, astronomers found this picture. And it was a color picture. It was taken in multiple filters. And it takes a little while to kind of line up the stars, but this star and this star are this one and this one. This guy here is these two stars blurred together. And right sitting where the supernova now is, or now was, is this red star. And that red star looks exactly like Betelgeuse. And I mean, by exactly, it has the same color, which indicates the same temperature. It's red. And it's the same luminosity, probably about 100,000 times the luminosity of the sun, just 13 million light years away. To prove that that star actually exploded, you want to wait several years for the fireworks of the supernova to go away, and then get an after picture, and you see the star is gone. So it literally exploded as this supernova. And what this tells us time and again is that red supergiants do explode as supernovae. This is actually the kind of forensic work that I have done a lot of, just studying the sites of stars that explode. It's always after the fact. The star explodes, and then you get excited and look in the archive and find a picture of that part of the sky. And we always find that these stars are red supergiants before they blow up. in other galaxies. So I love studying progenitor stars. And that's why, as they're called, the progenitor of the supernova. And that's why Betelgeuse was so exciting to think about studying, because we know it's going to explode. It would be really neat to study one of these stars actually in detail before it explodes. And it just sits there beckoning us. So we have great observational evidence that Betelgeuse is going to explode. Question is, when? And then why did people get so excited at the beginning part of last year? To understand the answers to these questions, let's take the first one. When is it going to explode? To understand this and our uncertainty about this, we have to delve into the heart of the matter, which means going to the core of stars like Betelgeuse. The part we see, the surface, okay, is just maybe an indication of what might be happening in the core. But all of the real action that triggers an explosion is actually in the cores of such stars. So to understand why some stars die by exploding, let's first understand how stars live their lives. And remember again, a star like Betelgeuse or our sun is just a big ball of gas, but it's big and has a lot of mass, and gravity is always trying to compress the star and shrink it. I mean, if gravity had its way, it would just compress the star all the way down to a point. That's what gravity wants to do. But while a star is living, there is a very strong pressure force pushing out against the gravity of all that mass. And it's basically the pressure of light itself, the force of light itself. Believe it or not, light exerts a pressure. And in the cores of stars living their lives, there's a tremendous energy generator generating a tremendous amount of light, which actually pushes against the outer layers of the star and keeps them puffed up. It opposes gravity. And these two forces, gravity in, pressure out, keep the star nicely puffed up during its life. And stars are essentially made out of hydrogen gas to begin with. It's the simplest and by far the most abundant element in nature. You remember your periodic table, one proton sitting in the nucleus. And when our universe began 14 billion or so years ago, there was hydrogen and not much else. And so stars are basically just big balls of hydrogen held together by gravity. And what's so simple about hydrogen is there's just one proton, positive charge, sitting in the nucleus. And what we understand is happening in the cores of these stars is that hydrogen nuclei are whizzing around so fast because it's incredibly hot there. And occasionally two hydrogen nuclei overcome their mutual electrical repulsion. And when they get close enough, they stick together to form the next element on the periodic table, which is helium. And whenever that happens, a bit of light is given off, a bit of energy. And that's basically the secret. In the cores of stars, light elements are being fused into heavier elements through this process called nuclear fusion. And it's a tremendous amount of light. It's actually that light that pushes out against the outer layers of the stars and is ultimately released by its surface that keeps the star puffed up. The problem is a star is born with a limited amount of fuel, hydrogen. And elements heavier than helium can be fused into, but they need even higher temperatures because there's more protons to jam together, so there's more electrical repulsion. So once the core of a star, like our sun, is done with hydrogen, it needs to find a new fuel source, and stars like our sun do. Helium can then fuse into heavier elements like carbon and oxygen, and so forth. But for stars like our sun, and in fact for 399 out of every 400 stars nature makes, it kind of ends right there. The temperatures never get hot enough to be able to fuse elements heavier than carbon and oxygen. And the star actually dies at this point. This is going to happen to our sun in about 4 or 5 billion years. The death is rather gentle. Here's a picture of a dying sun-like star. There's the star, and here is what used to be attached to the star. They actually blow off in a gentle wind the outer layers of the star, and then the star itself compresses down to a really, really dense object that gets supported by a new form of pressure support due to quantum mechanics. Basically, electrons don't like to be squeezed too close to each other, and they resist very strongly. and you wind up with this corpse of a star, maybe the mass of the sun, but about the size of the Earth. So it's shrunk about a million times in its volume. And this is the fate that awaits our sun, actually, in 4 or 5 billion years. These objects are called white dwarfs, and we see thousands of them littering our galaxy, these corpses of once magnificent stars. But nowhere in that story is there an explosion. For that, we have to consider the very rare stars, about 1 out of every 400, that happen to be born with more than 8 times the mass of our sun. That's kind of the cutoff. Their fates are entirely different. And what makes them different is that after they fuse hydrogen into helium and then helium into carbon and oxygen, the temperature in the core gets hot enough to fuse heavier elements. And so they don't quit there. They're able to actually manufacture elements all the way up to iron, which has 26 protons in its nucleus. But at that point, quantum mechanics gets in your way, because it turns out that you can't fuse elements heavier than iron. It doesn't give you energy, it requires energy. And so it's no longer a source of fuel. During this process of fusing all the way up to the element iron, it's a tremendous release of energy as you get to those heavier and heavier elements and those higher and higher temperatures in the core. And the star actually gets much more luminous, meaning more pressure pushes out against the outer layers. And it's during that phase, towards the end of its life, where it swells up and becomes this supergiant star. And that's the stage Betelgeuse is in. It is done fusing hydrogen in its core and is now fusing heavier elements. All right. It's a very precarious state once you start fusing heavier elements in the cores of one of these supergiant stars. And it's precarious because you wind up with this really interesting structure of the star, a big, thick hydrogen envelope surrounding this tiny core, which has the ashes of all those times of fusion in the core, building all the way up ultimately to an iron core. But this is a very bad place for the star to be, because you can't get blood from a stone. You can't get energy out of the element iron. And so at this point, the star is stuck for a fuel source. And when the iron core becomes massive enough, probably about 1.5 times the mass of the sun, gravity gets its victory, and it catastrophically collapses this core. In about 1 second, that core goes from something the size of the Earth down to something about the size of the city of San Diego, if I can use a local analogy. And at that point, the core halts in its collapse when a form of pressure support similar to the one that supports a white dwarf is found. But it's actually due to neutrons. Protons and electrons get squeezed together and form a ball of neutrons. And they also don't like being squeezed close together. And so they resist further compression. And what's called ultimately a neutron star is formed in the core of the star. This happens in less than a second. And the rest of the star, after this core collapse has just happened, falls in without that core supporting it, smashes into that proto-neutron star. And best we can understand, a shock wave develops that pummels its way out through the envelope and ejects it into space. And you have the birth of a supernova explosion. And it announces itself with a brilliance of probably about 1 billion times the luminosity of the sun. This is the exact fate that awaits Betelgeuse, just like it does every red supergiant. The problem is the timing of the event. We know by virtue of the fact that Betelgeuse is a red supergiant that it's done fusing hydrogen in its core, but that's about all we know. The problem is it can fuse helium for about 1 million years. The rest of the stages go by very quick. Carbon gets fused for a few thousand years. If it's fusing neon in the core, it's got only about half a year. If it's fusing silicon into iron, it's only got like a day left. The problem is we can't see the core. And so we don't know what's happening in the core. We see the surface. And so we get very excited if something strange starts happening to its surface. Okay, and that's exactly what started happening to Betelgeuse at the beginning of last year. So let me tell you the story of what we saw on the surface of Betelgeuse beginning at the end of 2019 and then into 2020. Being about the 10th brightest star in the sky, Betelgeuse has been observed for thousands of years. And going back as far as into the 1800s, astronomers realized Betelgeuse, in fact, is not a constantly bright star. It varies in brightness. And so for the past 100 years or so, we've been keeping very close track of how Betelgeuse has been varying in brightness, how it appears in the sky. And I'm going to show you a so-called light curve of Betelgeuse from the past 7 years or so that just show you how it goes up and down in brightness over the course of a year. So this is the light curve of Betelgeuse, courtesy of the American Association of Variable Star Observers. Each point is an observation going back to 2013. Typical brightness is about here on the plot, and you can see it goes up and down. Half as bright as typical would be somewhere around here. And you can see Betelgeuse has some pretty big excursions from its normal brightness. By the way, you might notice there appear to be gaps in the observations. Are observers just getting sick of observing Betelgeuse every year around the same time? Nope, you probably guessed it. That's when Betelgeuse goes behind the sun and we can't see it. So we can't observe it for a few months of the year in the summer months. You'll note I chopped off the end here, and that's because that's when Betelgeuse did this. And that got people really excited. It plummeted in brightness, way dimmer than we'd ever observed it in the historical record before, down to about a third of its normal brightness. You could literally just look in the sky, and if you were used to looking at how Betelgeuse usually looked, you noticed that, here's a little movie, that it was getting really dim. It became like the 30th brightest star in the sky. So it was really dim. And this is what led to all the excitement and even hyperbolic speculation last January. So this kind of just went on even into February, as people were getting very excited that maybe this dimming was telling us something about its imminent demise. By the end of the month in February, people were getting really sick and tired of the fact that it wasn't exploding. And so even articles about distant cosmic explosions would come with the tagline, "No, sorry, it's not Betelgeuse." Okay, so people were getting really antsy. I mean, they just joined the rest of us who have been waiting for this thing to explode for many decades. The problem was with such a prediction, of course, is that the trigger for the explosion is in the core of the star. It's not on the surface. And just because the surface was dimming, most astronomers didn't think that was really telling us anything about the core. And the main reason, the big reason is these stars are so big, any change in the core conditions would probably take hundreds of days at least to reach the surface and cause any noticeable change there. Furthermore, astronomers scrambled into the historical record to just see, do we notice red supergiant stars fluctuating in brightness wildly right before they explode? And an article came out looking at historical data of these kinds of supernova explosions, finding their light curves in the years before they actually exploded by looking at that progenitor star. And what they found is there was no significant evidence for variability right before the explosion. So at least in the ones we could study, and it's just a very few where we have this kind of record, there wasn't so much sudden drops in brightness. So at this point, people started kind of giving up on the idea that Betelgeuse was imminently about to explode. Although, you still would get the occasional headline like this. But reports of this imminent demise became tamped down, especially when we waited so long that Betelgeuse returned to its normal brightness. And so it was right back where it usually was. And that's what you see here by April or so of 2020. In case you're wondering what it's been doing since then, just yesterday I downloaded the most recent plots of its variability, and you see it's just sort of bubbling around its normal brightness. Okay, it hasn't done another dramatic dip again. But the questions remain, when will this thing explode? And it turns out that the last article I showed you, kind of jokingly, it actually did get it right if you read the article, and it's good it did, because it interviewed me for the thing. So it says, any day now or night, the red supergiant is expected to explode and go supernova, any day that is within the next 100,000 years or so. And to be absolutely truthful, if I really had to cover my bets here and be conservative, I would say pretty sure it's going to explode in the next million years. If you really forced me to a precise answer, I'd say 100,000 years from now, best chance. And this is just based on some surface chemical composition evidence that gives some clues to the stage of its life. But unfortunately, the best I can really do is it's sometime in the next million years. Keep watching. It wouldn't surprise me at all if it blew up today, really 500 years ago, but we'd see it today. But it also wouldn't surprise me if it took 500,000 years to explode. So as of now, our estimates are still pretty vague, but pretty precise for an astronomer. It does leave us the second question. Why did it get so dim? Why did it get so faint? I mean, this was really unprecedentedly faint. If you just paid attention to if you have just been paying attention to the popular press, you'd probably think we've answered this question already, because you can find titles like this, Mystery Solved, many times in the popular press going back over the last year. Okay, finally explained. The problem is, if you really keep looking at the popular press, you find more truthful articles saying that we're still stuck knowing why it got so dim. Let me give you the Cliff's Notes version of why we think Betelgeuse got so dim last year. We don't have that many clues. I'm going to give you the single best clue that we have to its antics a year ago. And it involves an update to that great picture I showed you from January of 2019. This was before all the strange stuff started happening, before the dimming episode. We got another picture of Betelgeuse during its dimming episode. And so I'm going to show you this picture. It was taken in December of 2019, just as it was plummeting down to its minimum. And take a look. Remember, this is a resolved image of the surface of Betelgeuse. So this was January of 2019. Here is December of 2019. January, December. Wow. I mean, I was amazed when I saw this picture. It seems it was not like an overall dimming of its surface. It was something that seemed to just really affect the southern hemisphere of the surface of the star. What could cause this? The debate has really settled around two main possibilities here. Basically, the possibilities are the southern part of the surface of the star became a lot cooler. Cooler things give off less light. That's one possibility. Another possibility is something started blocking or shielding our view, preferentially of the southern part of the star. To put it in more scientific terms, we say either the surface temperature of the southern hemisphere dropped, or in astronomy, the number one candidate for something blocking our view of something is dust. A dust blob in this started covering the southern part of the star and dimming our view of it. Let's interrogate these two scenarios a little bit. First, let's interrogate this idea that maybe the southern part of the star just dropped in temperature, the surface part dropped in temperature. And to kind of understand the theory there, let's take a look at our sun. It's a little movie of our sun, showing these famous sunspots that Galileo discovered back in 1609. Blemishes on the surface of the sun that we now understand to be regions of cooler gas on the surface. They appear darker because cooler gas emits less light than hotter gas. And so the patches of our sun that have sunspots appear darker. Less light is given off. For a star like our sun, these regions are typically fairly small compared to the size of the star. Okay, I say small, but each of these spots is about the size of the Earth, but that's small compared to the enormity of the sun. Stars like Betelgeuse, these red supergiant stars, have huge convective zones, and star spots on such stars are much bigger even compared to the enormous surface area of these stars. Here's a simulation showing kind of what we think if we could see the surface of a star like Betelgeuse would actually look like. And the idea is maybe a gigantic star spot appeared on the southern part of the star, leading to less light being released for a time. Okay, so that's kind of the essence of the temperature change argument. The southern part of the star just became much cooler for a time due to a very large star spot. The other idea that star was just fine, but there was a dust cloud blocking it. Okay, you might think this sounds kind of odd, but we do know that stars do this. Stars do puff out material that eventually cools enough to condense into little dust grains, and ultimately the combined dimming power of all those billions of dust grains can shield and block our view of what's coming behind it. And so the essence of all of the different papers that have been coming out over the last year and a half, the titles might look kind of complex, but they all kind of boil down to these two competing arguments: temperature versus dust. And you can see this sort of playing out in, now these are the actual scientific papers. Let me kind of walk you through a history of these scientific papers that have come out. This starts all the way back in March of 2020, during the dimming. The first article to come out: Betelgeuse just is not that cool. Effective temperature alone cannot explain the recent dimming of Betelgeuse. And this is an argument for dust, because that's the other thing we know could be dimming it. But you will look at the literature a little bit later, another article comes out: photospheric temperatures of Betelgeuse during the great dimming of 2019-2020, no new dust required. Okay, so there you have an argument against it. And then you wait a little while, another article comes out: a dusty veil shading Betelgeuse during its great dimming. Okay, this article, which is quite recent, was followed almost immediately, and interestingly, by the same journal publisher, the Nature group of journals: spectroscopic evidence for a large spot on the dimming Betelgeuse, arguing here that the dimming episode is caused by the dropping of its effective temperature again. So it goes back and forth, back and forth. At the risk of getting a little geeky here, let me just talk about a little bit about what this means. I showed you pictures of Betelgeuse. That's one form of data we get. What's this spectroscopic evidence for a large spot? What is spectroscopy? Here is a spectrum of Betelgeuse. I'm particularly proud of this spectrum because it's the first one that we took at Mount Laguna Observatory after struggling for a year and a half. So this was really beautiful when we got this spectrum. This was taken back in January of 2020. What are you looking at here? Isaac Newton taught us that if you pass light through a prism, it disperses it into its colors. We learned that those colors correspond to wavelengths. And so you could replace these kind of academic labels here with more human-friendly ones of color versus relative brightness. This is the color of Betelgeuse as a function of, this is its relative brightness as a function of its color. And what you immediately notice is Betelgeuse is red. Big surprise. It gives off most of its light at red wavelengths. But more importantly, you see all these dips in brightness at these different colors. This is what's so beautiful to an astronomer. These are the signatures of different elements and molecules in its atmosphere, like magnesium, barium, hydrogen, and especially a molecule known as titanium oxide, that actually removes light at certain colors or wavelengths. And modeling these stars' atmospheres has yielded the fact that the cooler the star, the deeper these absorption bands become. And so a key thing when searching for temperature decreases is to just get a whole lot of spectra of the star. And this is what we've been doing and continue to do, okay? And other groups have done, getting spectra of the star. It's a very tricky analysis, I'll say, of these. These are our first 3 successful spectra. It's so tricky that I've sicked my graduate student, Robert Baldoki, on it. He's going to be graduating, fingers crossed, this semester, okay? And he's been analyzing all the spectra we've got. And I'm not going to steal his thunder by presenting his particular conclusions in this argument. But until he does, okay, present these, he's coming to some interesting conclusions about the temperature of Betelgeuse. Until then, and I can't be so bold as to say we're going to settle the complete debate, but honest reporters will tell you that yes, we're still stuck on the exact reason Betelgeuse got so dim. But we have pictures and we have spectra, and the fact that we're still stuck and it's a gnarly problem is kind of what makes science so fun. So at this point, if I'm being honest, we don't know why Betelgeuse became so dim, but we do have some ideas and some candidates that hopefully we'll be able to eliminate more of in the time to come. So let me just sum up. Bottom lines, when will Betelgeuse explode? Sometime in the next 1,000,000 years. Count on that. If I'm a betting man, I'd say 100,000 years from now is the good time to try to figure out how to be alive. It could be tomorrow though, so don't be surprised if it does. Second question, why did it get so dim? We don't know, but we do have some definite ideas. Star spots and lowering temperature on the surface or dust, maybe some combination of the two things. That's often what happens in science. So just invite me, or probably better, Bobby, back in a year or so, and maybe we can answer that second question. And of course, if Betelgeuse has exploded, you'll all know about it, and you won't need us to tell you that that's happened. So I see my time is up, so I'm going to stop there. And if you have any questions, I'm happy to take them.
Dr. Leonard, excuse me, Dr. Leonard, thank you very much. Wonderful discussion. And everybody, we can turn on our microphones and ask questions. Anybody got a question?
Yes, this is Chuck. I've got
Hi, Chuck.
two questions. Hi, 2 questions, Doug. The first is, this is not the first time that we've seen this type of dimming. I see other dimming in the light curve that you showed. This is certainly the deepest.
Yeah.
Is there any periodicity in these dimming cycles?
Yeah.
And
Keep going.
And the second question will be, this dim has a very sharp cusp to it. Does that lend any credence as to which of these 2 or other mechanisms could cause the dimming? I wouldn't see a massive sunspot to produce a cusp like that in the dimming?
Very good questions. So periodicity has been detected. You can run a periodogram over these data, and people argue about what the exact periods are of the dimming, but there is sort of a primary period of something like 400 days for the dimming, and then some claim a much longer term dimming over several years. And it does, and some argue that this big drop kind of was both of the long-term and the short-term dimming happening kind of coincidentally at the same time. Though that's arguable, not sure that that's true. What's causing these is another debatable question. Most argue for some kind of stellar pulsation mechanism happening in the surface of Betelgeuse, but it's an open question why these red supergiants, some of them are quite variable like Betelgeuse, others are not. And so, not surprisingly, we don't have great answers to that. As to, what could produce such a sharp cusp? Does a star spot do it versus dust? Both of these mechanisms kind of seem like they have trouble producing such a sharp cusp, as you say. To be absolutely honest, if you ever want to get an astronomer really squeamish, just ask him or her what causes sunspots. We know it has something to do with magnetic fields, but in astronomy, there's an old saying, the stronger the magnetic field, the greater the degree of ignorance on a subject. And that's certainly true. We don't have any kind of model that suggests there should have been a huge, confluence of magnetic fields producing a big star spot then, other than the fact that star spots are really big on the surface of Jupiter, surface of Betelgeuse. And it's plausible that one or more of them over the time scale of several months could have appeared and gone out. So other than a plausibility argument, I don't have anything great to give you. And this is sort of fundamentally at our level of ignorance of what produces star spots. And in terms of dust, this is also a problem. I should say, kind of the evidence for dust has at this point been the absence of other evidence. If you believe the temperature didn't change that much, you're kind of left with dust. And the fact that we do know giant stars do, pardon the expression, belch out a lot of material once in a while. We don't know why, like Eta Carinae in the 1850s pushed out a whole lot of material that eventually cools down and becomes dust. And so a dust blob is not totally unrealistic as a dimming mechanism. But the actual sharpness of this raises some interesting questions. We are going to be very interested in, we're coming up again to, the next spring here in 2021, going into 2022. And, we'll definitely want to be paying attention to Betelgeuse to see if it engages in another big drop like this. So this is a long way of saying, Chuck, we don't know.
Hey, Doug, if I could ask, I keep thinking about the people who've gotten PhDs from studying the thermodynamics in a coffee cup. And you might have answered my question, but let me phrase it. If one would look at a star, the question simply is, and I think you've answered, how well do we understand the mechanism and how well can we model it of the behavior, internal behavior of a star? Because you've got thermodynamic effects, probably physical motion from rotation, magnetic effects, maybe in lack of homogeneity in the material itself. So all those things might combine in very difficult ways to understand, and given the purposity of data would actually receive, since we can't penetrate the star, how well is all that understood, and how much confidence would you have in models to explain phenomena like this? Yeah.
Good questions. These are all great questions, and you're kind of on the cutting edge here. It's okay. So first of all, let me just point something out about Betelgeuse that I have to admit I didn't know before I started studying it so carefully. I always knew that these red supergiants have very slow rotations. I didn't know how slow. The sun basically rotates once a month. It's like a 30-day rotation. Betelgeuse, our best estimate for its rotational period is 36 years. I did not know it was that slow. 36 years. So one sort of variable that you don't have nearly as much of when you're studying convection and stuff. And I'm looking here for my nice slide of the simulation, is very fast rotation, because you just don't have that in these humongous stars. But the way I'd characterize it, and I'm no expert on stellar interiors, okay, but I think in its broad scope, we understand convection and radiation and conduction in stars well enough to understand that at this stage of the life in a red supergiant, the envelopes have become convective. And given those conditions, the convective cells are very large. But the details, like I said, if you want to make an astronomer squeamish, just ask them to explain sunspots. The details of how this all happens to produce sunspots or star spots, that's very complex. I'm certainly no expert. And, we have theories to explain that, but I wouldn't say we're that confident of all the details of those theories. So as usual, a lot of ignorance. That's what makes it fun.
I'm looking at this graph here, and the time period I see is sort of probably on the order of an academic study. Probably the time period depends on the funding for this study. Do we have, but Betelgeuse has been observed naked eye for, I don't know, 1,000 years, something like that. Do we have a longer term graph like this where probably we might be able to see some of these big dips? Is there any sort of longer term graph of Betelgeuse's light curve?
Yeah. So again, I'll say that what I'm showing you here is courtesy of mainly amateur astronomers, the American Association of Variable Star Observers, who go out and measure the brightness. And so we have these kinds of records going back several decades, but we do have naked eye observations, and there are publications that attempt to get the historical record, definitely going back into the 1800s, not nearly to the level of precision we have here, where the AAVSO folks have actually done differential photometry using CCDs or photomultipliers, estimating the brightness. But we do have visual, just eyepiece observations going back into the 1800s, enough to know that this is unprecedented. Okay, we have not seen that before, at least going back into the 1800s. Now, we don't have such good records going all the way back, 1,000 years. But as far as we know, this kind of dimming has escaped the historical record. But there are publications, I don't have them handy, that attempt to reconstruct this going back at least close to 200 years.
The good old AAVSO.
Oh yeah, it's really it's kind of amazing. I mean, one of the things I discovered, like I said, is professional astronomers tend to eschew these really bright objects. We're always arguing to get time on the world's biggest telescope to discover the faintest things in the universe, and the brightest stars turn out to actually be quite tricky to observe using even a 1-meter telescope. Like we have at Mount Laguna. In a sense, it's overkill, but it's also really hard because it's so bright, it saturates your detector very quickly. It helps that we have a horrible spectrograph that has awful throughput. That's actually what got me thinking, like, what could we use the spectrograph, which is a horrible spectrograph, at MLO. Horrible meaning the throughput's just awful. And then I realized that has one advantage. You could actually observe a really bright star and without saturating. And it turns out you can.
We've had a couple of questions come in on the chat. Can I put those into the conversation here? Shri Ann asked again about the rotation of Betelgeuse's surface. 36 years, I guess there's not much of a relationship, but does the spectrum of Betelgeuse show the composition of the dust? And Blaine asked if the James Webb telescope will help show that composition.
Oh, that's a good question. All
right, great questions. And this may partially tip my hand here. I've tried to be agnostic on the cause of the dimming. Let me take if I can unpack that. The question about, does the spectrum show evidence for dust? So the answer is no. What's basically posited, so there are no specific spectral features that the dust adds. The dust is posited to be what's called gray dust. And this is getting kind of geeky into astronomical terms. But what gray dust is it's postulated that the grains are so large that they actually extinguish all wavelengths of light basically equally. So it's kind of the perfect crime, because the theory is it just dims the whole light of the star at all wavelengths. Gray dust is often invoked when you can't come up with some other reason for something dimming, because if you say it fades all wavelengths of light equally, it's virtually undetectable, other than the fact that it dims the star at all wavelengths. So no spectral features, and it just provides an overall dimming of the light coming from the star. So the initial papers on the dust suggested it was gray dust, and this was mainly due to the fact that at optical wavelengths, it seemed to be dimming in broadband filters like B, V, R, and I relatively equally at all wavelengths. A difficulty has been that more recently, infrared data, and you mentioned the James Webb telescope, that's going to be largely an infrared telescope. Infrared data seems to show that the star didn't dim nearly as much at infrared wavelengths as it did at optical wavelengths. And this is a little uncomfortable for the gray dust theory, because at optical wavelengths, a cooler surface means deeper titanium oxide bands, means less light given off at optical wavelengths, okay? There are not titanium oxide bands in the infrared part of the spectrum. And so not seeing dimming at infrared wavelengths, okay, is an argument against just an overall dimming. It may be that at visual wavelengths, the flux was diminished due to these absorption bands, actually, and that the temperature decreased a bit, and that does decrease the overall brightness of the star, but much less so at infrared wavelengths than where there are these molecular features. And so a difficulty for the dust is you start having to fine tune it a bit to try to get it to absorb at shorter wavelengths and not absorb so much at longer wavelengths. So it becomes a little uncomfortable. And that's kind of tipping my hand to the idea that temperature might be the thing driving this whole thing and not dust. I will say, let me just give you the absolute latest. Literally last week, a new paper came out with a very interesting idea, just to add a third possibility to this whole thing. that kind of is a perfect cure for all the things. And the idea of the paper is that maybe Betelgeuse ejected some gas, hasn't condensed into dust, but this ejected gas, this material that's just sort of parked in the circumstellar region, floating very slowly away, is actually cooling, and itself is what is absorbing all this light from the titanium oxide bands. And so the actual surface of Betelgeuse may still be okay, but the actual light being removed is from the cooling circumstellar gas. It's a really interesting idea. Seems kind of hard to refute, but it's yet a third idea for what might have caused the great dimming. And of course, this gas would be postulated to just be blobby releases covering the southern hemisphere. So very interesting idea. So people are still throwing out new ideas. Surface temperature, dust, and now blobby ejections of gas is also in the mix.
But wouldn't ejections of gas like that be quite visible, even in relatively small telescopes, by which I mean maybe meter or a couple of meter-sized telescopes?
No, remember the images that I'm showing you of Betelgeuse, these small telescopes cannot produce these images. In other words, where you're resolving either the surface of the star or even the vicinity of the star, gas leaving it. This requires something called adaptive optics and very specialized techniques using much larger and better equipped telescopes. So no, you can't hope to actually see these ejections in such images, but spectrally we might be able to witness them. And this paper is very interesting. Did modeling of, what if you have a gas cloud, not a dust cloud, a gas cloud, shielding the southern hemisphere. And at least in their models, they got these very deep titanium oxide lines, even with the surface temperature of Betelgeuse staying relatively the same. So, like Facebook likes to say, it's complicated.
It's complicated.
But you will see the press saying we've solved it, 10 more times this year. And rest assured, we probably haven't, but there's a lot of interesting ideas out there. That's why we're still studying it.
I've got one other question in the chat from Paul C, who doesn't have a microphone. And Paul wants to know, suppose we had just a huge, efficient way to observe neutrinos. Would neutrino observations, theoretically anyway, help us know what is happening in the core of a red giant star?
Great question. And yes, the answer is yes. Our only window into what's happening right now in the core of a star like Betelgeuse is actually neutrinos. And because, okay, let me just sort of back up. A supernova like the type that Betelgeuse will be one day produces a lot of stuff in addition to light. And in a sense, the light is actually a sideshow to where most of the energy is in a supernova explosion. Most of the energy of a supernova is actually liberated in the form of these ghost-like particles known as neutrinos. Ghost-like because they go through just about everything, like every good ghost does, goes through walls and people and stuff. So they're often called the ghost particle, but we can detect them. They're very hard to detect, okay? And they are predicted to be produced in abundance in a supernova explosion. And it's not just theory at this point. The closest supernova of the last 500 years occurred in a nearby dwarf galaxy known as the Large Magellanic Cloud, only 150,000 light years away. And we managed to detect about a dozen neutrinos of the billions that flowed through the Earth when that event arrived at us. And so we actually detected the neutrinos from that supernova. Okay. Betelgeuse is much closer than that. And so our detectors would be swamped with neutrinos when it explodes. But leading up to the actual core collapse, okay, in the hours and days before the core collapse, is an increase in the neutrino production. And so, yes, if we could develop neutrino detectors sensitive enough to detect the pre-supernova increase in neutrino flux, we would get some indication of Betelgeuse being about to explode. We don't have that yet, but folks are developing a whole network of neutrino detectors to definitely capture the neutrinos from the next galactic or Milky Way supernova. And the hope is eventually to get them sensitive enough to maybe give us a warning for when this is about to go. So that's a very good question. It is our one way of seeing into the core of the star. That's how we see literally into the core of the sun. We have detected solar neutrinos. The only neutrinos we've detected from a source other than the sun is this supernova called supernova 1987A. But it is our best hope to actually someday be able to know what's going on in the cores of nearby stars.
Fascinating. Thank you. Please, other questions? Anybody else got a question? Silence. Then if I could ask a question, if a star needs to be 8 times as massive as the sun in order to end in a supernova explosion, how much more massive still does a star need to be in order to end in a stellar mass black hole? And does that happen? Can that happen?
Excellent question. All right. So you won't be surprised when I answer, we don't know, but we have a theory. So we know nature does it, okay? We know that nature takes stars, very high mass stars, and turns them into neutron stars, okay? And explodes as a supernova, okay? We have direct evidence for the existence of neutron stars at the locations of historical supernovae. Okay, that one in 1054 is known as the Crab supernova. And sitting right there is a neutron star that we've detected right at the location that 1,000 years ago people saw a supernova. So we know nature produces neutron stars. Most of us are also basically completely convinced that nature also does produce, and you use the right word, stellar mass black holes, meaning black holes of more than 3, 5, 10 times the mass of the sun. Okay, we know nature produces these things. At this point, we don't have any direct connection between the production of a stellar mass black hole and a supernova. And the theory, if I can just be very simplistic about it, the basic theory says, just like you intimated, you need a really high mass star to produce a black hole. General figures are something like 40 times the mass of the sun. With some special conditions, maybe you get down to 25 times the mass of the sun for the implosion to ultimately give you a black hole. The question of whether that implosion that ultimately produces a black hole also produces a supernova or just implodes directly to a black hole called a direct collapse, that's an open question. And astronomers argue about it all the time. And recently, observers have gotten into the game. Historically, we look for things that explode and get our attention because they're so bright. But just in the last decade, dedicated searches are being made for disappearing stars. What a concept. A star that's here today and then tomorrow is gone. We haven't usually looked for things like that, okay? But there have started to be dedicated searches mainly looking at the nearest galaxies, eyeing their red supergiants, and looking to see if any of them just kind of disappears. And that would be evidence for a direct collapse to a black hole without a supernova. And I'll say that right now, the searches have yielded one good candidate for a disappearing star. And so more work needs to be done on that. So the Cliff's Notes answer to your question is we know nature produces stellar mass black holes through the collapse of cores of massive stars. The theory says the star has to have been born with at least 25 and maybe 30, 35, 40 times the mass of the sun to end up as a black hole at the end of the day. But we do detect these black holes. And I'll just point out, we now have a new way to detect them. We used to detect them because they would, if that collapse happened in a binary star system, we couldn't see the black hole, but we could see this other star zipping around the black hole and occasionally feeding it with material that would give off bursts of X-rays. And so we proved the existence of the black hole by analyzing the secondary star orbiting it. In just the last 6 years, we now have a new way to detect stellar mass black holes. And that is through gravity waves, LIGO, the work that's done at Caltech. Because the signature of two black holes merging produces an enormous gravitational event. And we've now detected that signature many times in LIGO's detectors. And that's giving us actually really large masses, because they're the easiest to detect, of some of these stellar mass black holes, over 30 times the mass of the sun, which is a lot. So the star that gave rise to that clearly has to be a humongous star to have given those. So black holes. I often think, wouldn't it be neat if Beetlejuice just went out? Like, we're all expecting this gigantic supernova, but wouldn't that be interesting if one day there was just no shoulder in the constellation of Orion, and Betelgeuse was just one of these disappearing stars? That in some ways would be even more dramatic to astronomers, anyway.
Well,
And not out of the question, okay?
yes.
Because we don't really know the mass of Betelgeuse, to be honest. I said 20 times the mass of the sun, but that number is very, very shaky at best. Some estimates come in a lot lighter than that.
That's fascinating. That's absolutely fascinating. I think it's fantastic. Mike, why don't you take the last question, because we're getting on in time.
Is the Vera Rubin Observatory going to produce the kind of data that will allow us to look for disappearing stars?
That's a really good question. Generically, the answer is yes. Any observatory that takes repeated pictures of the night sky, okay, is good for doing this kind of work. So I think the answer is yes. Question is, and I'd have to look into, the actual projects that are being proposed on the Vera Rubin Observatory. There's very particular kinds of observations you want to be taking. You can do the work with, generally the work's been done with whatever happens to have been done randomly. A systematic search for these disappearing stars is tricky, especially in a telescope that's more designed for a wide field survey.
Mm-hmm.
You kind of have two choices when you're conducting, surveys. You can either observe a wide swath of the sky at pretty low resolution, or you can observe a small patch of it with high resolution, right? And so the best searches for disappearing stars need the small patch with high resolution, because you have to be able to tease out the individual stars in the nearby galaxies, and that's actually really hard to do. So I know the dedicated searches for disappearing stars have employed high resolution imaging. Systematic surveys will detect supernovae very well. With the new LSST and all, all the different surveys coming online, we expect to discover a lot more supernovae. Don't think we're expecting to discover a lot more disappearing stars, and I think it's mainly because of the resolution issue. You need to really do high resolution imaging, and most of these surveys are designed to capture the whole night sky relatively quickly rather than a small patch of it. So yes, many more transient events like supernovae, an order of magnitude more in the coming years and decades. But disappearing stars is still kind of a niche field. So I think I'm going to end up with that answer for it.
Well, thank you very much. And Dr. Leonard, you've been very gracious with your time. And I think we're kind of running over here, but been a great presentation and a great discussion here in the questions. And I thank you very much for that.
Thank you. And thanks everyone for, I'll stop sharing my screen. Thanks everyone for coming on your Saturday morning. I will say it's nice to be giving a talk in my own time zone. With these Zoom talks, I give talks in India and stuff, and I'm having to, get up at weird hours in the morning to give the talks. It's nice to actually have one that's at a convenient time for me. So thanks for the invitation, and I hope to see some of you up at Palomar or come visit us at Mount Laguna whenever we get back to being in public again. Hopefully this all ends pretty soon.
Hopefully it all ends pretty soon. And let me also note that Dr. Leonard's course reader, Principles of Astronomy, is available from Montezuma Publishing. So
I don't recommend that unless you take my astronomy course.
Okay.
Feel free to buy it if you want, but it's really for my students.
I probably should have asked about that before. Oh, well.
It's a course reader specifically. It's interesting that you dug that one up. It's a nice course reader with nice slides.
Next time I'll check before I do that one. Anyway, we need to bring the meeting toward an end. Let me just mention the next talk, kind of as a preview. The Greenway Talks online will continue on Saturday, October 9th, when Dr. Bonnie Buratti, JPL Fellow and Section Manager and Senior Research Scientist at JPL, will tell us about the work she is doing on the Hale telescope to explain the geophysical processes that have shaped the surfaces of Pluto and Charon, and to document the activity that is taking place there now. She's doing follow-ups on the New Horizon mission. And finally, as we started at the beginning, as Catherine mentioned at the beginning, an important event that you should not miss takes place tomorrow afternoon, September 26th at 5 p.m. Pacific time. Timothy Thompson, Mount Wilson Observatory trustee, observatory docent, and session director, is giving the last presentation of this season in his series, Sundays with Tim. Throughout his talks, Tim has chronicled the history and achievements of Mount Wilson Observatory. And on Sunday afternoon, you can link to his presentation from the Mount Wilson website. Hey, it's been a great series of talks, and Tim, thank you very much. So, again, thank you to Dr. Doug Leonard. My thanks as well to all of you, to everybody here for attending and supporting the Greenway Talks online. And with that, I'll close the meeting, and I look forward to seeing you all on October 9th. Everybody, bye-bye.
Thanks, everyone.
Thank you.
Thank you. Great talk.
Thank you.
Thank you.